I'm Liz Beckman. Welcome to this part of the CT at 50 celebration on the technologies that were needed to enable CT, and an introduction into how these have rapidly changed to enable the scanners of today.
Hello, my name's Richard Waltham. In the summer of 1973, I had my first experience of CT scanning when I was working on a machine very like the one on the left in this slide, because I was an undergraduate student sponsored by EMI Limited, who were making these scanners. And I guess the scanner I worked on was something like the 7th one off the production line, so it was fairly early on in the process. And during that summer, I briefly met Godfrey Hounsfield, who was the pioneer of this technique. And the following year, when I graduated, I went and joined his department. So anyway, we're going to talk about CT technology and how it's changed in the last 50 years from the left of this slide to the right of this slide. The four main technologies which are needed by CT is to generate X-rays, detect X-rays, of course, but also a new thing for CT was to convert the X-rays into numbers. Then you've got to mechanically move the X-ray beam relative to the patient, or if you wish, you can do it electronically. And you've finally got to reconstruct the data and display it as the radiologist wishes to see it. The second and fourth items on that list have been revolutionized by what in electronics is known as Moore's law. And that means that if you look at the power we've got today, it's about 6 million times more power from silicon chips today than there was available in 1976. And that's just a staggering increase. And CT has benefited very greatly from that, as we shall see later on. Back in 1969 or 71, the scanners that were being used experimentally then had bulky photomultiplier detectors, which were needed because they were the only detectors with adequate performance in terms of the noise performance and the dynamic range. But they had a very low packing density, which meant that you couldn't make, for example, you couldn't make the sort of array of detectors which goes on a CT scanner today. And that enforced a traverse motion, a linear motion, or a motion across the image. This is the first CT scan of a patient, which was 1st of October 1971. And I'm going to use this scan and the scans by the prototype in the previous slide as kind of markers on a timeline. In the top left of this slide, there's a time chart, and the two little blue squares are marks for the first CT scans in the laboratory, scanning excised tissue, and the first scans in the hospital, scanning clinical patients and changing the patient management for them. Above them, there's three important changes in the first decade of CT. In the early years of CT, the assumption was that you'd have to process the image reconstruction, not in the hospital, but on a centralized site for that particular region, on an expensive mainframe computer like the one on the right-hand side, the ICL 1905. That assumption ceased to be true around 1973, when mini computers became available, and they were much more compatible with being used in hospitals. They didn't need to be in a dust-free, air-conditioned room, and they didn't have the huge bulk of the machines you can see on the right, and they didn't need highly trained operators. The second bar, in fact the second two bars, are related because the photomultipliers implied the transverse motion, as we've discussed previously. And they faded out in around 1978 as better detectors became available and compatible with the performance needed for CT scanning. The final bar there is magnetic core memory. And that's a change which actually affected, it was inside the mini computers. Their memory in the early days was magnetic core memory, which is shown at the bottom left. And around 1977, it became possible to replace that by semiconductor memory. And that had two benefits. One is it was smaller, took up less physical space, but also it was obviously a replacement because it was lower cost. So that was an important change. Several important changes, in fact, in the first decade.
Here you can see the specification of the original EMI Mark I CT scanner. At the time, this was a stunning achievement, but it appears very basic to us now. The scan time was between 4.5 and 20 minutes per scan. It's true that this was for 2 slices at a time, but compare this to the 22 to 25 seconds to scan a complete 1,500mm area along the body today. And with multi-slice capability, typically this gives us up to around 320 slices per scan. Scan time for one rotation in a modern rotate-rotate gantry is of the order of 0.3 seconds. In the original Mark I scanner, 160 readings were required for each linear traverse of the gantry across the patient. The gantry then indexed by 1 degree before translating back across the patient, acquiring another set of 160 readings. This process was repeated for 180 degrees. The thickness of each slice in the Mark I scanner was either 8mm or 13mm, and the detectors were sodium iodide crystals paired with photomultiplier tubes. A stationary anode X-ray tube had to be utilised, since rotating anode X-ray tubes would not cope with the mechanical impact at the end of each linear translate motion. Over the years, a significant array of X-ray tubes and tube technology have been developed and used to optimize the performance of CT scanners. From the original stationary anode tubes used in the Mark I scanner to modern high-spec rotating anode tubes, such as that used in the Canon Aquilon scanner, shown on the bottom left here. One of the challenges of using stationary anode X-ray tubes in the first CT scanners was significant heating issues. Modern rotating anode X-ray tubes not only have much higher heat storage capacity, but also higher heat dissipation. Here you can see an example of the sort of specification needed in a modern tube and power supply for CT. Of course, in addition to the high heat storage and heat dissipation requirements, with the speed of rotation of modern CT gantries, modern X-ray tubes have to be designed to withstand very high G-forces. Over the time since the 1970s, there have been significant technology improvements in many areas. This includes liquid metal bearings, cooling fins on the anode, and the routing of secondary electrons to a separately cooled electrode so that they don't go back onto the rotating anode and increase the heat on that. While there have been improvements within X-ray tube technologies, in some ways these have been fewer major changes here than in some other areas of CT technology. As Richard has said, the original lathe bed and early scanners used a mechanical geometry where there was a linear motion of the X-ray tube and detectors relative to the sample or patient being imaged. In the lathe bed, it was the sample that moved linearly across the path of the X-ray tube and detectors and was then rotated by 1 degree before travelling back across the X-ray beam. In the clinical scanner, it was the X-ray tube and detector that moved, translated across, and then rotated around the patient.
Now we're going to talk in a bit more detail about detectors, and this is just a reminder of the fact that the photomultipliers were the earliest detector. They use this translate and then rotate motion, which is shown schematically here, and they were soon, in fact, in sort of late 1970s, replaced by xenon detectors and silicon photodiodes. On the left here, we've got a photodiode detector with a scintillator above it. And on the right, we've got a xenon gas detector. In fact, what we've got is 4 xenon gas detectors side by side. And there's some interesting similarities and differences between these. In both cases, you get an X-ray photon arrive through the top of the detector, and it creates multiple particles. On the left, it creates multiple visible photons, and those are caught by the photodiode at the bottom and produce an electrical signal. On the right, it creates multiple ions. It splits the xenon gas into ions, positive and negative ions. And because there's a voltage difference between the blue tungsten septi and the dotted red collecting electrode, you get the ions migrate down as an electrical signal coming out of the bottom. But the interesting word there is multiple. You get more electrons out than you put photons in, and that's extremely useful in getting your low noise, being able to amplify the signal electronically without introducing noise. So multiple electrons for one X-ray photon is a similarity between the two sides. But the big difference, I think, is in the density of the materials. The scintillator is a solid, it's a crystal, and it's actually quite a heavy, dense crystal because it's made of heavy atoms such as cesium iodide or cadmium tungstate or whatever. On the right, the material is xenon gas, and even though it's xenon gas under quite a high pressure, it's still a heck of a lot less dense physically in sort of grams per cubic millimeter than the scintillator on the left. So you end up needing a very long path of gas compared to the path of scintillator that you need to stop a decent proportion of the X-rays. And that has consequences in terms of crosstalk between the detectors, and to try to mitigate that, you end up with a shorter piece of xenon gas than you might otherwise have, and that would cause lower dose efficiency in the detector. And basically it's turned out now that using a scintillator is currently preferred to using a gas. The next thing you've got to do in a detector is to convert the signal into numbers. And again, this changed quite a lot in the early days of CT, because before about 1978, there was no integrated circuit method of doing this in one chip. And in the early days, Hounsfield and the other pioneers had to make their own detector out of many simpler components. And Hounsfield's method used about 60 components per detector, which made it quite bulky as a piece of electronics, and didn't help the cost. Hounsfield used the dual slope integrator method, which is shown by those diagrams. And those who are interested can read how it works below. So these days, we can pretty much have what performance we need. But the challenge is still quite a big challenge in terms of analog to digital conversion. The dynamic range is a major challenge, because there's a huge difference between the number of photons which would travel through a 500 millimeter body, a fairly obese patient. And if you take that patient out, the same number, a far larger number of photons will emerge through the air that's left behind. There's a number of ways of easing that. Still used today, but pioneered back in the 70s, is a wedge filter, or a bow tie as it's sometimes known, which mitigates the fact that you know that in the outer regions of the scanned field you cannot have such a long tissue path as you can in the middle. So you put in this bow tie filter for two reasons. One is to limit the dynamic range a bit, and the other is to make the dose across the patient more uniform, because otherwise you're putting an awful lot of dose into the outer parts of the scanned volume where you don't actually need it. In the head-only scanners that were available in the early days of CT, the problem, of course, is greatly eased by two things. One is the head is smaller than the body, and the other is it's very, very unusual for people to grow large fat deposits on the outside of their head. The other technique that was used in the very first scanner was a water box. The patient put their head inside a cup of, effectively a flexible cup of water, and that meant that basically the dynamic range was reduced to almost nothing. Another big problem with detectors, or a need for performance, is that the noise from the detector electronics must not dominate the noise from the X-ray photons. Otherwise, again, you're wasting dose, and we really do not want to do that. Then the conversion has to be fast, and particularly with the fast rotation times these days, the requirement to read each detector several thousand times per rotation means that it's quite a challenging task to do this conversion to numbers at high precision and at high speed. And finally, but last but by no means least, if you've got a rotate-only scanner, which is what all the modern ones, or the vast majority of the modern ones are, then stability and linearity in the conversion is very important, otherwise you get ring artifacts. It is a major challenge, and it's grown over time because of the increased number of slices in the cone beam and because of the reduction in scan time. But then we go back to the Moore's law tailwind, which applies to some extent in detectors, although they're not the real mainstream silicon products like processors and memory, which Moore's law definitely applies to. Today's CT scanners have a detector module which contains both the detectors and the electronics to convert the signal into numbers. And that's very useful because it avoids having long wires between the detector and the electronics, and those wires would otherwise be prone to pick up unwanted electrical noise. And that applies both to the xenon detectors, which there's a diagram of at the top left, and to a silicon detector, which you can see an early version of down at the bottom left. Initially, the xenon detectors were the more dominant in the CT marketplace, but that was because they were very stable. But silicon detectors have now caught up in stability and win out in terms of crosstalk and more dose efficiency.
One technology that did not exist at all in the early days of CT, but which has become essential to enable the continuous rotation of the X-ray tube and hence spiral CT, is slip rings. While there were less technical barriers to the development of slip rings than in other areas of CT, and there have been less changes in the technology over the years, it is still a key and essential technology for the modern CT scanner. A really key technology that has grown significantly over the years with huge benefits to CT are computers and algorithms. Computer power and speed has increased exponentially, starting, as we've said earlier, with the large mainframe computers of the 1960s, such as the ICL 1905 that the first CT scan images were processed on, to the mini computers such as the Data General Nova and Eclipse, which were in the early production EMI head and body scanners. By the late 1970s, dedicated array processors were being used to process the CT images. Over the following decades, computers and processors have got smaller and more powerful till integrated circuit processors were available with far more power and speed than an entire building of the early mainframe computers.
The algorithms have improved, and I've just put a couple of examples there of ways in which they've improved. If you talk to the CT manufacturers, they probably give you a much longer list of that, but these are the ones that sort of I've noticed, basically. When Godfrey Hansfield launched CT scanning in 1971, he estimated that it was about a 100-fold step, 2 orders of magnitude, I think was how he put it. You could argue whether that was exactly right, but it was a very big step from the previous technology of plain X-rays. So what's happened since then? Well, instead of looking from 1971 till now, I'm going to look from 1981. So that we skip the first decade when things like photomultipliers and central mainframes and core memory technology, magnetic core memory technology, were fading out of the picture. So if we just look from 1981 till now, that 40-year period, I'm going to give you some very rough estimates, and I'm sure you won't agree with all of them, but these are my rough estimates and you can make your own. I think probably the patient throughput has improved by about a factor of 3. Of course, the patient throughput is held back by things like porterage, patient handling, and it's not purely a matter of if you halve the scan time, you double the patient throughput. And that improvement in patient throughput is important, and it's come from improved detectors, more detectors, and from improved X-ray tube and more power from the X-ray tube. And in the case of rotating anode tubes, the ability to keep the tube running for longer, more heat capacity in the tube. I've written there that there's been a 3-fold increase in spatial resolution, which would mostly be from improved detectors, although X-ray tube may have made some contribution to that. I'm not sure that it's actually as big as 3 times, because actually the spatial resolution was already reasonably high in 1981. But let's leave it as a number of 3 just for now. And lastly, but probably most importantly, there's been a 4-fold improvement in dose, by which I mean dose efficiency rather than increasing the dose on the patient. And that, I think, is mostly attributable to improved detectors and improved algorithms. So if you just multiply 3 times 3 times 4, you get 36. So if we've got a 36-fold improvement over 4 decades, that means that it's been doubling about every 8 years. The performance of CT has doubled in that 8-year period. So you could say it's 4 times slower than Moore's law, but Moore's law is an unfair comparison because that only applies to silicon, and it only applies within the silicon chip industry to those chips which are absolutely the highest volume.
Thank you for watching this section on early CT technologies as part of the celebration of CT at 50.